Hello, you're welcome to lesson 2 of structural steelwork design course. Alright, so today I'll be teaching you on steelwork connection, but first it is very essential that you understand or have a theoretical background before we go into calculations. So what are steel connections? Steel connections are expected to be designed based on realistic assumptions regarding the distributions of internal forces, considering the relative stiffness of components. These assumptions should align with direct load paths through the connection element. So it is very important to ensure equilibrium with the externally applied factored loads, and then to ensure that this equilibrium is maintained. Now, what are the things that you should ensure when you're designing a steelwork connection? Number one, it is expected that a steelwork connection should be rigid enough to prevent fluctuating stresses that could lead to fatigue failure. Another one is to minimize weaknesses or the weakening of the connected parts. Also, to be easy to install. The ease of installation is an important thing. The ease of inspection and also maintenance. And the steelwork joints are needed to connect individual frame members together. For example, a beam to column connection, beam to beam connection, for example. These are essential, and that's why we're dealing with connections. And also to link plates and sections in built-up members to ensure composite actions. So it is important to note that connection joints are designed to transfer axial loads, shear, moment, and torsion. Now, a pin joint transfer axial loads and shear, while a rigid joint, just like we understand for reinforced concrete sections, transmit all forces. And what we mean all forces: horizontal, vertical, and the moments. Sliding joints are designed to undo reactions where expansions is accommodated. Alright, I have a video that would show you what connection exactly means. So if you peradventure don't have a full understanding what steelwork connection means, this very short video should show to you what exactly we're talking about here. So this is the connection, you see, and these are layouts. All right, showing to you every part of the arrangement: diagonal truss members, vertical truss members, and then look at the plan. You see that now we're showing the bolts around the secondary truss, and that is it. You see, so this is exactly what a steelwork connection is, and we design for it. So if your desire is to know how to design a steel connection as this, then this course is for you. All right, so there are various kind of steelwork connections, or various methods we use in achieving steelwork connections. One of it is a bolted connection, the use of bolts in making connections on steelworks. So, and also there are three common types of bolts used in structural steelwork, and they are black bolts, the close tolerance bolts, and also the high strength friction grip. Of course, you would have seen somewhere HSFG bolts. So these are the three common types of bolts that are adopted in structural steelwork connections: the black bolt, close tolerance bolts, high strength friction grip bolts. And then there are different characteristics. Why do we use them? What are their features? Why are they essential? Why are they different? You see that now. So I have a figure of the black bolt right on my screen, on the right part of what you're viewing. That's the black bolt. These are rough unfinished bolts that do not have precise shank dimensions. All right, they are typically used in situations where slip and vibrations are not critical. They are not critical. So they are also installed in holes with a nominal clearance of 2 millimeters and are available in both mild and high strength steel. All right, so this is very common. You would have seen black bolts. You would have seen that. Another bolt that we use is close tolerance bolts. These bolts are designed for use in applications where slip and vibrations are not acceptable. You see that now, almost the same as black bolts. But then, what's the uniqueness? They are precisely machined and fitted into carefully drilled holes with a nominal clearance of no more than 0.15 millimeters, which for black bolts is 2 millimeters. So close tolerance bolts are available in mild or high strength steel also, and their material classifications is defined by a specific grade. So we may, pardon me, we may say that the difference between black bolt and close tolerance bolt is the fact that the nominal clearance for black bolt is around 2 millimeters, but for close tolerance bolt it should no more than 0.15 millimeters. What of the HSFG bolts? That's the high strength friction bolts. These are bolts used in situations where strong joints are needed with bolts under shear or tension in simple designs. Also, in rigid designs, connections must transmit large moments along shear and axial load. So it's also applicable in that case. They are made of high tensile steel and used with high tensile units and hardened steel washers. So what the steel washers are, the things you're seeing that looks circular and flat in between the two ends. All right, so those are the washers. All right, so they are tightened to a specific shank tension, creating a clamping force that transfers load through friction between the connected parts rather than relying on shear or bearing on the bolts or the piles of the connected components. All right, so I have two tables here on my screen. And why do I have them? These tables shows the shear strength of bolts and the bearing strength of bolts. And as we go along in teaching, you discover that um, the bolt or the strength of a bolted connection, all right, is either in shear or the bearing capacity. So we need to understand the shear strength of bolts and also the bearing strength of bolts for that. So if you're designing a bolted connection, for example, you should pay attention to the shear strength of the bolts and also the bearing strength of the bolts, so that you can be able to pick the appropriate bolt grade, and the numbers. Okay, so table 30 shows the shear strength of bolts, and we have three major grades of bolts: the grade 4.6, grade 8.8, and grade 10.9. All right, and these have respective shear strengths, and as you can see on table 30, and table 31 shows the bearing strength of both, the same both grades but different bearing strength this time. So for grade 4.6, the equivalent bearing strength is 460. Grade 8.8 equivalent strength is 1000. For grade 10.9, the equivalent is 1300 Newton per millimeter square. All right, so we have the classifications of bolted connection. We are discussing bolted connection, and they can be classified based on the type of resultant force transferred. All right, so we have three different types of connections under this, which is essential that you know, because when we start to do the calculations now, we'll make references to all of these things, because what type of connection it is would actually determine what approach is required to designing that connection. So the first we have is the concentric connections. All right, what do we mean? That the force transfer is in tension and compression members. You see that now, the usual tension and compression. All right, and we also have the Now the concentric connection is what you're seeing in figure 1 below under A and B. All right, is either they are in tension or in compression. All right, so the A is seen together as in a joint, B is connected to a plate, and then to the truss member. All right, so the second classification is the eccentric connection. And why is it eccentric connection? All right, it has to do with transferring in reaction, transferring brackets. What you can see under eccentric connection ought to be figure 2 anyways, is the brackets or moment resisting connection. So when you're talking about um having an axial load to be transferred to a stanchion, for example, you see that sometimes we use brackets to receive the load and then transfer to the stanchion. In that case, you have an eccentric connection, seeing that the axial load is at a distance away from the centroidal axis. All right. And also we have the moment resisting connection. In this kind of which is also termed as eccentric connection. So we might not have to call it the third one. Sometimes you find in the case of beam to column connection, like I said earlier, um, it produces moment in that regard, and it is taken or treated as such. Okay, so in ideal concentric connections, which is the first one we discussed, we should only have one bolt passing through all the members meeting at a joint. However, in practice, it is not actually possible. So, and that's why we have figure 1b showing if the two members join together by a single plate under another truss member. However, in practice, it is not usually possible, so it is only ensured that the central axis of the members meet at one point. All right, so that's that. Now to discuss the strength of bolts. Like I said earlier, it is essential that we know the strength of bolts and the bearing capacity, because it helps you in picking what bolts and how many numbers of them in that connection. So the design strength of bolt is either in shear or bearing capacity. I told you, whichever is lower. So the capacity of one bolt, how do we determine the capacity of one bolt in shear? So that's PS, which is the shear capacity or shear strength, is equals to PS AS, as in clause 6.3.2 of the BS 5950 that you have already with you. And for grade 4.6, I already showed us on that table 30, and grade 4.8, and I already showed us all those things on the table 30. So the AS you see there is the shear area, and the shear area can be taken as the area of the bolt. For example, if you are using a 16 mm diameter bolt, it could be taken as the entire 16 mm being the diameter, or you just take only the tensile area, and you use the tensile area as defined in 6.3.1 of that code. So make reference to that. Okay, so also the capacity of bolt in bearing, which we call the bearing capacity of a bolt, according to clause 6.3.3.2 of the same code you have with you, could be obtained using the relation PBB, which is the bearing capacity, is equals to D, the diameter, TPBB. That's the thickness of plate is TP, and then we have BB, the bearing. You see, PP is the bearing strength of the bolt obtained from table 31. Okay, TP is the thickness of connected parts of plate if the bolts are countersunk. The thickness of the part minus half the depth of countersinking. It is essential that you have an understanding of all these things that have been trying to communicate, so that by the time we're starting our calculations, you already have the flow of thoughts, so you can actually link with whatever it is we are teaching. Also, the tension capacity of a bolt. We've talked about the shear strength, we've talked about the bearing capacity, and now we have the tension capacity of a bolt. Now, the bolt subject to tension. The tension capacity of a connection using bolts, including 90-degree countersunk head bolts, should be checked using one of the following methods. So there are two methods according to our BS code. All right, we have the simple method and we have the more exact method, and I'll be showing you the two of them there. All right, the simple method says that we can obtain the tension capacity P norm um, to be 0.8 PT, which is the tension strength of the bolt, multiplied by 80, which is the area, the tensile stress area, as specified in the appropriate bolt standard. All right, but for bolts where the tensile stress area is not defined, area of T should be taken as the area of the bottom of the thread, like I said the earlier time. Okay, so that's clear enough, I believe. Okay, then we have the more exact method, the second method. So the more exact method can be used for connection in which both of the connected parts satisfy one or more of the following. So if the connected part spans between two or more supporting parts, the outstand of the connected part, when we say outstand, we mean probably a flange, a connected member forming a flange of a butte member, you understand. So, and the outstand of the connected part is designed assuming single curvature or double curvature. Okay, so the formula is PT tension capacity is equals to PT, that's the, like I said, the tension strength defined in table 34, all right, multiplied by 80, which is the tensile stress area. All right, that's the more exact method. Okay, we also have bolts in tension and shear. That's the moment connection. I told you about the moment connection when I was describing the three connections on the bolted connections: the eccentric, concentric, and then uh, the moment connections. Okay, for the moment connections, we have them to be a combination of tension and shear. So when you have a combination of tension and shear, there are also formulas to use. We have simple method and also we have the more exact method. So you see these two methods as shown on the screen, and note that PS in this case is the shear capacity. All right, so and the FS is the shear. All right, so we have the bolt spacing. We are still under bolted connection anyway, and we have bolt spacing. There are informations that you should have handy before you start your calculations if you want to get it correctly, and that's why we're doing this theoretical background. Okay, so the minimum spacing for standard clearance holes or holes for fitted bolts, the spacing between centers of bolts should not be less than 2.5D. Please note that the spacings between two centers of bolts should not be less than 2.5D, where D is the nominal diameter of the bolt. For oversized holes or slotted holes, the oversized spacing should be increased to leave at least the same width of steel clear between the holes as for standard clearance holes. All right, so we have gotten the information that the spacing between center of our bolt should not be less than 2.5D. So as you go, this is a very reasonable information that you should hold. Now the minimum edge or end distance, there's a minimum distance at the edge and the end. All right, so the minimum distance from the center of your bolt to the edge or end of any part should not be less than the value in table 29, and table 29 is shown on this screen now. All right, so we are dealing with a road. I told you in the first lesson that the method of production of steel um is either cold rolled or hot rolled. So you understand now. So for rolled machine flame cut, sun or plain edge or end. So the end distance is 1.25 d. So everything you are applying in your calculation, the end distance should not be less than that 1.5 d if you are dealing with a rolled um machine flame cut, sun or plain edge or end. All right, for sheared or hand flame cut edge or end, it should not be less than 1.4 d. So we have the maximum edge or end distance, maximum edge or end distance. Where parts are connected by bolts, the distance from an unstiffened edge to the nearest line of bolt should not exceed 11 T epsilon. 11 T epsilon. This does not apply to bolts interconnecting the components of back-to-back tension members. All right, where the parts are exposed to corrosive influences, the edge distance should not exceed 40 millimeters plus 4 T. All right, so we know that the maximum edge or end distance we're dealing with should whatever distance we are dealing with in our work should not exceed 11 T epsilon. 11 T epsilon. So please note all of these things we said. As we start our calculations in the next class, we'll bring practicality into all of this knowledge. All right, so we have the maximum spacing in unstiffened plate. Where a plate is not stiffened by a web or outstand, the spacing between centers of adjacent bolts in a line lying in the direction of stress should not exceed 14 T. You see that now, this is the maximum, should not exceed 14 T, where T is the thickness of the thinner element. Now the edge and end distance, of course, we've spoken about this. All right, so and there are references to 6.3.3.3 and 6.4.4, um which are in the code of practice that you have together with you there. Now, if there are other questions you would need to ask, I'll be willing to answer to you. You will be doing well to go over this lesson and understand all the theoretical background, because in applying it in our next class, it will take that you understand, it will require that you have understood everything that we have said so that you can have a flow together with me. See you in the next class. Bye.